So here today we will study the crystal oscillator. In a last lecture, 2 lectures, we studied the LC oscillators and RC oscillator. Under LC oscillator, Colpitts and Hartley we have studied, and RC oscillators, RC phase shift and Wein-Bridge oscillators we have studied. But now if we see the LC and RC oscillator, these values will vary depending upon the temperature, and output frequency also varies. Now if voltage fluctuates, if input voltage fluctuates or if the temperature varies, then the output frequency may change. So if we want a constant output frequency, more stable output frequency, then we need to use the crystals. Now what is crystal? Basically crystal oscillator works on the piezoelectric effect. Now what is piezoelectric effect? So when we apply the piezoelectric effect is a property that when the mechanical stress is applied on one of the phases, then the potential difference will be induced in the opposite phases and vice versa. If we apply the potential difference, then it will generate the mechanical stress or it will vibrate. So this is the piezoelectric effect. So based by using this phenomena, these crystal oscillators are designed. Now generally the examples for these piezoelectric materials are Rothschild salt quartz. Quartz is a very cheap and widely available material. That's why mostly we use the quartz crystals. Now this is the construction. Now if you see here, here between two metal plates, so crystal is mounted. So crystal is mounted between two metal plates. So this is called the crystal. This is a symbol for the crystal. When we apply the AC sine wave, then it will vibrate, and when whatever the now naturally designed frequency, whatever the frequency is there, if it is matching with the AC applied frequency, then the resonance occurs. Now this is about the crystal oscillator. Now so we will see the symbol and equivalent diagram for the crystal. So this is the crystal symbol, just we have discussed. Between two metal plates, if any piezoelectric material, nothing but if quartz is placed, then this is called the crystal. This is a symbol for the crystal. And equivalent diagram, if you see, here R, L, C values are connected like this and in series with the Cm. Now this is the frequency response curve for this equivalent diagram. Frequency, now here on the y-axis we have taken the capacitive reactance and inductive reactance separately we have taken. Now one more diagram, the same for the frequency response. Now this is one more diagram. Here on x-axis we have taken the frequency like the previous diagram. But on y-axis we have taken the impedance. Instead of taking the capacitive reactance and inductive reactance separately, now here I have taken the impedance. Now if you see, now here the crystal is having the two different resonant frequencies. One is series resonant and another one is a parallel resonant. Now this is the series resonant frequency and this is the parallel resonant frequency. Series resonant frequency is 1 divided by 2 pi. Now if you see the crystal, now L, C, R values are in series. Now this is R, L, C, and it is connected, Cm is connected like this, Cm. So this is the equivalent diagram for the crystal. Now this Fs is nothing but series resonance is nothing but 1 divided by 2 pi root Lc. Now this L value and C value is considered for the series resonant frequency. Now coming to the parallel resonance frequency, it is also 1 divided by 2 pi under root of LCT, where CT is nothing but, now here if you see C and Cm, both two capacitors are there. If we take the series combination of these two capacitors, CT is equal to C into Cm by C plus Cm. So series combination of these two capacitors, equivalent capacitance if we consider, then that is the parallel resonance frequency. Always the series resonance frequency is less than the parallel resonance frequency. If the frequency of the crystal is in between these two, that time crystal acts like an inductor, and if the frequency is less than the Fs or greater than the Fp, then it acts like a capacitor. So now we can use this crystal as an inductor or capacitor depending upon the frequency. If the frequency is in between these two values, then at the time crystal acts like a inductor. If the frequency is less than Fs or greater than Fp, that time the crystal acts like a capacitor. So by using this, we can design the crystal oscillator. Now in the So this is the Colpitt's crystal oscillator, nothing but it's a Colpitt's oscillator only. Now here we are replacing the inductor with the crystal. Just now we have discussed that. So if the frequency of the crystal is between Fs and Fp, then the crystal acts like an inductor, we have studied. So when we can replace that inductor value with the crystal, thereby what? Here if you are taking the inductor, then the inductor values will be there may be the aging effect, or there may be, depending upon the temperature, values may vary, and we don't get the constant output frequency values. So if we replace the inductor with the crystal, then here we get the more stable frequencies. And for this, now operation is like a Colpitt's only. Only the difference is what? We are replacing the inductor with the crystal, and the formula for it is same, 1 divided by 2 pi root L into Ct, where Ct is a series combination of this L1 and C1 and C2. Now this is about the Colpitt's crystal oscillator. Now if we wanted to design crystal Hartley oscillator, that time this tank circuit, here we have to take one inductor, here also we have to take one inductor, L1, L2, and this is C. At that time the crystal is acting like a capacitor. So that time F is equal to what? F is equal to 1 divided by 2 pi under root LTC. Now where crystal is a capacitor and two inductor values are used. So to avoiding the inductor means what? Here we can reduce the number of problems, like the cost, size in weight of the circuit, and also fluctuations, frequency fluctuations. So many things we can avoid if we avoid the inductor. That's why we go with the Colpitt's crystal oscillator. Simply we are removing we are replacing the inductor with the crystal. Now this is about the crystal oscillator. What are the advantages of crystal oscillator? So here if you see, the crystal advantages are, they have a high order of frequency stability, and the quality factor of the crystal is very high. So crystal oscillators are compact in size and are of low cost. So these are the advantages of crystal. Thank you.